Hello everyone, and welcome back to Virtual Thermodynamics. So today we're asking a pretty fun question, and that question is, what do we need to fly? So we've been looking at Brayton cycles, and it turns out we can use the Brayton cycle at the core of a jet engine. Now when I ask my daughters, what do we need to fly? They might tell me that the answer is faith, trust, and pixie dust. But as engineers, we know that what we need to fly is lift. So we get lift when we have a wing that's moving through air. Now, what happens is we create high pressure beneath the wing and low pressure above the wing, and that pushes a plane up in the air and gives us lift. But in order to get that lift, the wing has to be moving through the air. So in order to generate lift, we need thrust. And from thermodynamic perspective, we get that thrust from a jet engine. So when I ask, what do we need to fly? It's more like we need faith, thrust, and pixie dust. And today, we'll learn how to solve turbojet engine problems. So when we characterize the turbojet engine, it's a little bit different than all of the other heat engines that we've looked at, because here what we're trying to generate, the energy benefit, is thrust. Now thrust is a force, and it's given by the change in momentum over time. So I can get an equation for that and see that it's got to do with the mass flow rate of the fluid and the velocity of my air coming in and out. So I can get, knowing that the mass flow rates are the same, I can see that the thrust is mass flow rate times the change in the velocity of the air moving through my engine. So if I wanted to define a thermal efficiency, I would take my thrust on the top and my energy cost, which is again burning jet fuel. So that's going to be Q in. But we said thrust was a force, and I need power here. So how do I get power, or how do I look at thrust as a power? So here I've got to take my kilowatts, which is kilojoules per second, or kilonewton meters per second. So if I have a force in kilonewton meters, I have to multiply that by a velocity in meters per second. So my thrust power is going to be a force multiplied by a velocity. So I take the thrust force generated by my engine and multiply it by the jet velocity, and I get this equation. So if I was looking for an efficiency of my turbojet engine, I probably want to look at the cost of burning fuel, right? So that's going to be Q in, and that's going to be my denominator. So my thermal efficiency is thrust power divided by heat in, which is given by this equation. One of the tricky things in these turbojet problems is that the velocities that we find are relative to the moving frame of reference. So we have to think of ourselves as someone who's maybe standing on top of the wing of this plane as it's flying through the air. Because really, the jet is moving through the air, but we want to think about it as if the system is in sort of this, is our moving frame of reference. So we're sitting on the turbine or maybe on the wing, and it's the air that's flying into our faces. So the jet velocity is going to be the velocity in, provided that we think about still air. We're trying to maximize thrust. So to do that, we want to get the velocity coming out of the nozzle at the end of our turbojet as high as we can get it, because that's going to maximize our thrust. Now, in the center of our jet propulsion, or our turbojet engine, is a Brayton cycle. Now, the thing that's special about this Brayton cycle is that we only run the turbine enough so that it can power the compressor. So my back work ratio here is equal to 1, because I want as much enthalpy in the exit of the turbine as I can, because I want to convert that enthalpy to kinetic energy leaving my nozzle at state 5. So if we did the first law on all of our components here, we would get some equations that we're used to, like in the compressor, the combustor, and the turbine, but some that we don't usually see in thermodynamics because we're often neglecting the change in kinetic energy. When we look at the diffuser and the nozzle, we see that kinetic energy is important in these cases. Now, usually in thermodynamics, we neglect the change in the kinetic energy. But in this case, we're going to assume that the kinetic energy inside the engine at state 1 and at state 4 is negligible, but that the kinetic energy or the velocity term outside the engine at state A and state 5 or E, that those kinetic energy terms are important. So we won't set those to 0. So the other thing that's tricky about this turbojet analysis when I'm looking at the characterization is that the term in the numerator here is in joules per kilogram, and typically when we calculate Q dot, it will be in kilojoules per kilogram. So we have to watch out for units. As always, unit type problems are more difficult when we talk about the imperial measurement system. So here, when I take my kinetic energy terms, I also have to remember to divide by GC, which is 32.2. I do the same thing if I'm talking about the turbojet characterization here. Units are very tricky when we talk about these velocity terms. So now we're going to go through an example for a turbojet engine. I'll do this both with constant specific heat and with variable specific heat. So we're told that we're doing a turbojet engine. We're given the mass flow rate, the specific heat, and the pressure ratio from 1 to 2, so moving through our compressor. We're asked to fill out our state table and find all the relevant temperature and pressure data, to find the heat required into the combustor, and to find the velocity at the exit, which is state 5 in this problem. So here, if you look at my state table, I have a new column on the right that tells me what's the velocity. So I have the velocity coming in to my engine is 220 meters per second, and I'm trying to find the velocity at state 5 to solve the problem. So how do we solve the problem? What we're going to do, like we've done in many cycle problems, is kind of march through component by component and do first law analyses. So the first component here is our diffuser. The purpose of the diffuser is to maximize H1. So we're going to try to harvest the kinetic energy that's moving into the diffuser to try to increase the enthalpy as much as we can before our fluid gets into the compressor. Our first law looks like this. We'll assume that steady state, that it's one inlet and one outlet in our diffuser, that the change in potential energy is 0, that the diffuser is both adiabatic and passive, so it's well insulated and it's not generating or consuming power. And we'll assume that the velocity at the exit of the diffuser, so the velocity inside of our engine, is 0, or that the kinetic energy is no longer important inside of our engine. So now we can find the temperature at state 1. If I was doing a cold air standard analysis, then I'd know that my delta H becomes Cp times delta T. I have to notice that the units here are different, that the left-hand side will give me units in kilojoules per kilogram, and the right-hand side will give me units in joules per kilogram. So I go ahead and divide my V squared term by 1,000. Now, you can't just automatically divide things by 1,000 here, because you might be getting velocity in different units. So maybe not meters per second, but in miles per hour or kilometers per hour. So here I know Cp, I don't know T1, I know TA, and I know VA. So I can find T1 with a cold air standard analysis as 254 degrees Kelvin. For an air standard analysis, I'm going to find the specific enthalpies and not just the temperatures. I'm looking for HA in this equation, which I don't have directly, but I was told the temperature at state A. So I can go to table A22 and look this up, put it into my equation, and find a value for H1. When I know H1, I can interpolate and find T1 and PR1. I'm going to assume that the diffuser is isentropic. Remember, when the working fluid is air, it's very important to look for these isentropic processes because they'll hold the key for solving the problem. So, because this is an open system, I'm interested in pressure ratios and not volume ratios. So I use this equation in a cold air standard analysis. I put in the things that I know and I solve for P1. In this case, 36.9 kilopascals. I'll do the same thing for an air standard analysis, but here, when I have an isentropic process, I use this equation looking at PR ratios and pressure ratios. I can solve for P1 because I've already found PR1, and I can see that I get virtually the same pressure. So now I start to work into my Brayton cycle, which is at the core of my turbojet engine. Here, the tricky part to remember is that the back work ratio of this Brayton cycle is 1, that the turbine power is the same magnitude as the compressor power. First, I'll look at my compressor. In a compressor, I'll assume that it's steady state, 1 inlet, 1 outlet. I'll neglect changes in kinetic energy and neglect changes in potential energy. I'll assume that the compressor is adiabatic, but that it consumes power and that there's no friction or pressure losses in the system. If this is a cold air standard analysis, I'll change my delta H to Cp times delta T. I don't know the power consumed by the compressor, but I know everything else but T2. So now I'd have to say, okay, this is going to be an isentropic compressor, and I would use this isentropic relationship, which tells me the pressure ratio. I found the pressure ratio here, so I know P2, and then I can get an expression for T2 and find the value for the temperature at the outlet of the compressor. I'm going to use a similar process for the air standard analysis or the variable specific heat analysis. I'm going to assume that the compressor is isentropic. I'm going to use this equation with my ratio of pressures instead of an equation with K in the exponent. I'm going to get this expression for PR2. And when I know PR2, I can interpolate on table A22 to find H2 and T2. Now I'm going to want to move through my combustor. So now I'm burning my jet fuel and adding heat to my working fluid. Here, this component is steady state, 1 inlet, 1 outlet. We're going to neglect changes in kinetic and potential energy. We'll assume that the system is passive and that there are no friction or heat losses in the combustor. For my cold air standard analysis, I get this equation. I don't know Q dot, but I know Cp, T3, and T2. So I can just calculate Q dot here, and I find that with the mass flow rate, that Q dot, big Q dot, in the combustor is 22,392 kilowatts. In my air standard analysis, I know T3, so I can use that to interpolate and find H3 and PR3. When I know H3, I can put that into my equation. I know the mass flow rate, and I can find Q dot. Here you can see that I get similar answers, but there is some disagreement, about 11%. And that's because in the constant specific heat problem, I'm assuming that the specific heats don't change with temperature, but in reality they do. So the air standard analysis or variable specific heat analysis is more accurate because I'm making one fewer assumption. So after I've moved through my combustor, I can solve my turbine. It's important to remember here, this is where we use the fact that I'm only running my Brayton cycle so that I'm only running the turbine in my Brayton cycle so that I can run the compressor. Common assumptions here that we're at steady state, 1 inlet, 1 outlet, no change in kinetic energy, no change in potential energy, and that the system is adiabatic with no friction losses or heat losses. For my cold air standard analysis, I can get this equation. So this comes from the backwork ratio. So I'm setting my turbine power equal to the magnitude of my compressor power. So that's why I have the sign difference here, but both of these are in minus out. But I take the sign difference because I know that turbines are creating power, whereas compressors are consuming it. The CP's drop out, and I get an expression for T4. Now, I know here that I'm assuming that the turbine is isentropic. And if it's isentropic, then I can find the pressure with this equation. Usually, I do this the other way to find the temperatures, but in this case, I know the temperatures. So I have to do a little bit of algebra to find this equation. And I can get that the pressure at the exit of my turbine is 203.9 kilopascals. If I'm doing a variable specific heat analysis, I can use this same equation. I can solve for H4. And when I have H4, then I interpolate on table A22 to find PR4. Then I can use the ratio of the pressures and the ratio of the PR values to find P4. And from H4, I can also find T4. So now we're done with the turbine and we can move into the nozzle. So now, because our back work ratio was only 1 in our Brayton cycle, we have more enthalpy in the entrance to the nozzle than we otherwise would. Because what we're trying to do in this cycle is maximize the outlet velocity, or the thrust created by the jet. For our nozzle, we'll assume that it's steady state, that there's only one inlet and one outlet, that there's no change in potential energy, that the system is, or the component is adiabatic and passive, and that the velocity inside my engine, which is the velocity inlet to the nozzle, is negligible. So then I get the equation shown at the top of the page here. I got to remember to check my units. So because my velocity is in meters per second, I divide by 1,000 to get to kilojoules per kilogram. And then I'm going to get delta H is Cp times delta T, if I'm assuming that the specific heat is constant. My units match, but I don't know V5 and I don't know T5. So I have to use the assumption that the nozzle is isentropic. And if the nozzle is isentropic, then I can use this equation with K in the exponent to find T5. Here, I find that T5 is 638 degrees Kelvin. And I can use that temperature to find my velocity at state 5 in my moving frame of reference. And then to get the velocity in my stationary frame of reference, I have to take my velocity and subtract the velocity inlet to my engine, or VA. And I can find that in the stationary frame of reference, V5 is just over 790 meters per second. I can do a similar process for my variable specific heat analysis. Here, I again assume that it's an isentropic nozzle, so I'm going to use the pressure ratios, and I can find PR5 as 28.9. I can use that in table A22 to find H5, and then I can use H5 to find the velocity in the moving frame of reference, and then convert that again to the velocity in the stationary frame of reference. Notice again that these answers aren't exactly the same because I've made different assumptions depending on if I'm doing a cold air standard analysis or a variable specific heat analysis. So for my cold air standard analysis, my state table looks like this when I fill everything in. And for my variable specific heat analysis, I have more things to fill in because I have to find all my enthalpies. I really would have filled in the temperatures and the pressures here as well. And now if I look at my characterization, I can do this on both sides, remembering to check my units. And I get a thermal efficiency of just under 25 with a cold air standard analysis. But with a air standard analysis, I get 22.8. So they agree within about 10%. Now we always have to remember that the variable specific heat analysis gives us a more accurate representation of what's going on because we're making one fewer assumption. So that's the end of our turbojet analysis. Thank you for coming, and I'll see you next time on Virtual Thermodynamics.